Hey everybody, welcome to your next lab. This is a lab about testing for dissolved oxygen. So typically this lab would be part of lab number 1. It will be after we collected the water sample properly. We would then test it using reagents or an experiment in this test kit. This big black suitcase or briefcase is a test kit I took or borrowed, I should say, from work. And these are what we use in the lab for almost every single experiment except the air quality one. So this is a test kit. This briefcase is not something we created at the college. It's a pre-purchased kit from a company called Lamont, and they have a lot of different chemical experiments or tests you can purchase online, and one of them is water quality. So inside this briefcase, it's portable, which means we can take it to the source. You can bring this kit to the Corniche or a river or lake or swimming pool and test directly at the source, which we know is what we want to do. It's ideal because in transporting your water sample, you might be risking contamination or losing the integrity of that sample. I'll talk about fixing the oxygen in the sample as quick as possible in the next part of this video. So in the test kit, once I open it up, I'm not going to move my camera or lift the box or anything like that, but you should be able to see a number of blue boxes. Okay, these blue boxes are self-contained tests for different water quality parameters. So I have a pH, like an indicator test kit, water hardness, alkalinity, so again related to pH, sulfide test, carbon dioxide test, dissolved oxygen test, which we're going to use today, silica, chloride, ammonia, nitrogen, and then nitrates and phosphates. So 3 or 4 of these test kits we will use this semester in our online labs, more like demonstrations. So speaking of demonstrations, I'm going to demonstrate this experiment, the Lamont Dissolved Oxygen Test Kit. This test kit, this little box, is typically full of reagents and equipment, little beakers and test tubes and scoops. I have all of the equipment removed, ready for the next part of this video, but all of these boxes here are self-contained tests full of the reagents and equipment needed to do the experiment or do the test. So I'm going to pause my video here. I'll skip ahead a little bit and I'll have the experiment set up for us to do. So I have this set up here. I still have the box with a cutting board on top of it so I can lay my chemicals out and you can see them a little clearer. I'll try to do the best as I can for this. There are small numbers we're going to have to read with a little titrator. Again, I'll do that and share it with you. There are reagent bottles that we're going to add to our sample of water. There's color changes. Again, I'll try my best to show you this as I go through the experiment. So I have all of the reagents out of the box and I have my sample of water here. I'll explain where I got that in a minute, and I have the instructions ready to go. So this experiment, this test for dissolved oxygen, I am going to basically follow this. Okay, this is my lab manual, and like I mentioned, every experiment in here has its own instructions. This manual will be shared as a PDF online on the D2L content page and in the beginning of the quiz, the lab quiz. You will need this, or you will want to read some of this, wink wink, to answer some of the questions. It's a searchable PDF document. There's a lot of information here. There's pictures explaining what to do. There's the short kind of, I'll call it recipe or instructions on the back of what to do. And there's even a fact sheet about dissolved oxygen, where does it come from, where does it go, and then the method itself. The method we're using today, it's a chemical method called the Winkler method. The Winkler method involves an array of chemicals, which I will read them out to you now in a minute. And it's essentially a titration where we're going to see or measure the amount of oxygen in our water. So let me show you or explain where I got the water. I'll go through the chemicals, I'll do a quick pause, and then we'll do the actual experiment. So the water. This is a small sample bottle. It's a little different than the one in this kit. It requires a 60 milliliter sampling bottle. You'll see in the lab procedure it mentions the code number of the bottle. This is the same volume, same bottle, it's just a different brand. But this is full of tap water. Now in this experiment, we're going to measure the dissolved oxygen in tap water and a sample of bottled water. And I'm only going to do the demonstration for one of these, and then I'll give you the results of both of them to answer the questions. The tap water I filled a little differently than our method before, and this method is in the instructions. When you're filling from something like a tap or a bottle, a way to fill this without getting any water bubbles inside is to pour the water, turn the tap on, or pour it from the source until it's completely full and like really slow. You'll almost see the water kind of come over the top because of the surface tension. And then I put the top on there. So there isn't any air in this. I've completely filled it up and then put the top on. I, of course, washed this 3 times before I filled it up. Okay, so the reagents in the kit, I'll do a quick pause and then we'll do the experiment. Inside the kit, so besides the water that I collected, again, this is tap water. I have, in no particular order, sodium thiosulfate, starch indicator. This is alkaline potassium iodide. It's potassium iodide, and the alkaline part is potassium hydroxide. And those reagents are very important for the Winkler method. They're all important, but the name doesn't really explain what this is. So it's potassium hydroxide, that's the alkaline or basic part, and then potassium iodide. I have the manganese sulfate. They're using the old names for these chemicals. I'll explain the IUPAC names as I go through these. I have sulfuric acid. It's fairly concentrated. It mentions on the bottle it will cause severe skin burns and eye damage, but because it's in a dropper bottle, I'm going to be very careful when I add this to my solution, and if I spill any on my hands, I will immediately wash them with water. But because it's in a nice, easy dropper bottle, I won't take full safety precautions here. But if we were in the lab, I would have lab coat, goggles, gloves, especially if we were using large volumes of this acid. And other than that, in the test kit, I have a small bottle, a sampler bottle, which I'll get ready in a minute. I'm going to wash it first. And I have a little titrator. This is like a mini burette. I know it looks like a syringe. I mean, it is. But this you can think of like a mini burette. And it has numbers here, graduations, so we can actually measure the volume of the sodium thiosulfate, which will tell us the parts per million, ppm, milligrams per liter, of the dissolved oxygen in our sample. So I will explain how that is determined using the Winkler method in the next part of this video. So I'm just going to wash one of my sample bottles and make sure everything's ready and clean, and then we'll do the experiment. So not much has changed here. I just made sure that this was cleaned as much as possible. There is a little bit of water residue in this, but it is tap water, so it shouldn't affect my results. Now, a couple things before I get started. This is tap water in Doha. So I have let it come to room temperature. And I'm going to talk about temperature a little bit in this experiment because we know that temperature and the amount of dissolved oxygen, or I guess I should say temperature and the solubility of gases, is directly related. As temperature increases, the solubility of gas decreases. It's an inverse proportion, or it's inversely proportional. So the tap water here was very warm. You guys know the time of year it is. It's very hard to get cold water. So I collected the warm tap water. I let it run as long as possible with, the cold setting, collected it in the bottle, put the top on, and it's been about 30 minutes of me setting up, and this has reached essentially room temperature. It's important that this is room temperature so that it matches my bottled water in my second test, which is also room temperature. We want to limit any variables that are different. So keeping the temperature of these two the same by letting them be room temperature is really important for this experiment. In the notes, I talked about this the other day, and this, might come up in a question later, wink, wink. We know that 100% saturation of oxygen, we use Henry's law for that, and it's in your notes, but at 20 degrees Celsius, 100 degrees saturation of oxygen in the water is roughly 9 parts per million, 9.06, 9.07. This water is probably not 20 degrees Celsius. I'm going to take the temperature reading in a minute. So keep that in mind when we get our answers. At 20 degrees, it's 9 parts per million. I'm going to test the temperature of this before I get started to see. It should be, I think, 23, 24. Another thing we want to keep in mind before we get started is just remember where the dissolved oxygen comes from. This oxygen comes from absorption from the air, from the atmosphere, and photosynthesis from plants. So both of these samples of water are not really from natural sources. What I mean is I didn't go to a pond or a river or the Corniche and collect them. This is from the tap. It's been in pipes for who knows how long, or the storage tank out back, and this has been bottled for who knows how long. So consider some of these factors when I get my results. So again, I'll take a quick cut here. I'll get a couple more things set up. I'll get the temperature ready and we'll get started. I'm doing these quick cuts so I don't have to keep re-recording the video if I make a mistake. So just, hopefully you don't mind all these cuts. So this is a thermometer. It's for cooking, but it's a really nice thermometer. It's to 1 decimal place. It has pretty decent accuracy compared to some of the ones we use in the lab, like the big glass thermometers. It's maybe not as good as the LabQuest thermometer, but I didn't want to bring a lot of things home from work. So I'm going to turn this thermometer on. This is still closed. I am going to slightly break the rules here because I don't want to mess with a lot of glassware because I am in my kitchen and I'm not in the lab, but I am going to test the temperature of this water directly in this. Now I've cleaned this probe a lot, so hopefully I'm not contaminating this too much, and I'm going to do this quickly because one of the first things in this experiment is to fix the oxygen. Fixing the oxygen is, basically capturing the oxygen in another chemical format or another chemical substance. We're converting the oxygen to something new and capturing it so it doesn't interact with atmospheric oxygen. Meaning once I fix this sample, having it open to the air won't really affect my results. So I'm very quickly going to test the temperature with my clean probe here. And again, if this was in the lab and I had a bit more time and more glassware, I would test this separately in maybe a beaker or a test tube. So this water sample is 23.3 degrees Celsius. So it's a little bit above the 20 degrees that we talked about in class, where it would be at 9 ppm. So 23 and a half, roughly 23.5 degrees Celsius. Okay, so now I'm going to actually fix the water. I'm going to get the instructions open and we'll get this fixed and ready to do the titration. All right, so for this part of the video, this is the experiment, the Winkler method. Bear with me for this part. I might, stutter or kind of ramble or make a verbal mistake because I don't want to do this experiment in multiple takes. I have limited amount of chemicals that I don't want to waste. So this is kind of free form, but that's it. Well, you can pretend you're watching me do this in the lab in front of you guys. All right. So I'm going to follow my instruction manual, and the first thing I'm going to do is fix the water by adding my reagents. So the experiment is very easy. The experiment, the amount of drops and everything has been pre-measured, predetermined. It's basically 8 drops of all these reagents. It's really straightforward to do. So I want to fix this water as quickly as possible, and I might take a little quick pause and then we'll do the actual titration. So to fix my water sample, I'm going to add 8 drops each of 2 reagents. The manganese 3 sulfate. So I have the, where is it? This is called manganese sulfate, but it's manganese 3 sulfate. And I'm going to add my alkaline potassium iodide, 8 drops of each, and I'm going to cap it and mix it. Okay, so take my top off here and add the drops. Oops. Okay, put the top back on when you're done, so you don't waste any when you when you tip the bottle over. And so that was the manganese sulfate, the manganese 3 sulfate. Now I'm going to add that potassium iodide. Eight drops of that. And this is kind of interesting. You can see a color change immediately. I probably should have done that closer to the camera. And you can see a precipitate on the bottom of that. So I'm going to cap this now and mix that together. Again, you can see a precipitate on the bottom and like a yellow coloring. The precipitate is manganese 2 hydroxide, and that's a really important reaction or reagent in this experiment in the Winkler method. Now, the precipitate is white. It did form on the bottom, but this precipitate, the manganese, sorry if I say magnesium, manganese 2 hydroxide is immediately oxidized by the oxygen in this water. The oxidized form of the manganese 2 hydroxide is manganese 3 hydroxide. So this is the brown color you see here. So I got it capped, I'm shaking it right now, and I'm going to let that settle for a minute or two. I'll do a quick cut in the video. Okay, I didn't wait too long. You want to get this fixed as quick as possible. Again, when I say fix, I mean trapping that oxygen in. So when I take the cap off and do the experiment, I'm not introducing any extra oxygen into the water. So the next stage here is to add 8 drops. So it's 888 of sulfuric acid. Now this is concentrated. I'm going to be very careful. I'll do it kind of towards the camera here. The acid converts, and I'll talk about this conversion and what it means for the stoichiometry of this. The acid will convert our newly formed manganese 3 hydroxide. So remember, the manganese 2 was oxidized by all of the oxygen in here to form manganese 3 hydroxide. So there's a relationship there. And the acid will convert this into manganese 3 sulfate, which is the next chemical I need for my titration. This conversion fixes the oxygen in it. So all of that oxygen has been converted into a new chemical and won't affect our titration. The titration isn't with the O2. The titration is a new chemical that I'm forming. So any of the extra O2 that might come in here now when I take the cap off, once it's fixed, it won't matter. The titration with the sodium thiosulfate is not with the oxygen. It's with another chemical, which I'll talk about in a minute. So I'm going to add 8 drops. I'll cap it and gently mix it this time. We'll do another quick cut. So, okay, here's my chemical, 8 drops of sulfuric acid. So remember, manganese 3 hydroxide is a base. Hydroxide, I'm adding acid to this. So 8 drops again. So 1, 2. Okay, top on, put the acid away. I won't need this anymore. Put the cap on my bottle down here and give it a little shake. All right, you can see a color change. It went a little darker. All right, I'm ready to go. So before I actually do the titration, like I mentioned, this is fixed. So I could now maybe bring this back to a lab. The timing isn't as important now that I have fixed this solution. Again, oxygen might get in here, but it doesn't matter. That's not what I'm titrating anymore. So all of the oxygen that was in here initially has been captured as another reagent. So what am I titrating? Well, the iodide from the potassium iodide, this solution, the alkaline potassium iodide, is oxidized by the manganese 3 sulfate in here. And that creates free iodine or iodine, so I2, into the water. Now remember, all of these chemicals are related. I'm converting these chemicals from one to another. So the iodine created is proportional to the manganese 3 sulfate. The manganese 3 sulfate comes from the manganese 2 hydroxide and the oxygen reaction. So iodine is directly proportional to the amount of oxygen in the sample. So what I'm titrating here is the iodine in this solution, which is directly proportional to the oxygen that was in the solution. Okay, any oxygen now that comes in doesn't matter. The iodine, the I2, is what is turning this kind of yellowy brown color. Okay, kind of cool color here. Okay, on to the next part. Okay, this is harder than I thought. It's a lot easier in the lab with all of you guys. I don't know why, but anyways, I think I'm a perfectionist, and I keep doing takes for the same thing. But anyways, this is my little reagent bottle I mentioned earlier. What I'm going to do now is fill my fixed oxygen, or well, my sample with the fixed oxygen to the 20 milliliter line. Put the cap on. And then I'm going to fill my little titrator with the sodium thiosulfate, and then I'll do the actual titration. We're almost done, okay? So first things first, take this. I'm going to fill until the 20 milliliter line. Okay, so that's filled. I'll put the top on. The top has a little hole in it, so I can do the titration through this. And remember, because it's open to the atmosphere, it doesn't matter. The oxygen has been fixed. The other good thing now is I have more sample left that I could, if I make a mistake, hopefully I won't, but I could do another titration with this sample. So it's pretty convenient that this doesn't use all of this. If you wanted to do two, you'd probably get 3 titrations out of this. It was filled to 60 milliliters, so you could get 3 titrations. In the lab experiment that I'm putting on D2L, I'll give you my results from at least 2 titrations with the tap water and with the bottled water. Okay. All right, next part. This is the fun part. This is the part that students sometimes have a little trouble with, but again, not a huge issue. We are going to fill this titrator with the sodium thiosulfate. Okay, again, this titrator is just like a little syringe, a little burette like you would have done in 1200 or 1201, 1210. Now, this bottle here has another little hole in the top, so I can take the sample. Now, what I'm going to do with this sample is invert it. And actually, what I'll probably do when I do this is maybe because some of this can spill, I'll probably put on some gloves for this part and get this inverted and filled up. It's really important when I fill this up that there are no air bubbles in this at all. If you do notice air bubbles in this, You have to squirt, press the syringe, remove some, not back into this bottle. I would do it into a small glass or beaker. And again, try to fill this up so it's completely filled, no air bubbles. Air bubbles will affect our results. It will completely throw off our ppm because the volume in here is not recording accurately. So I'm going to get a pair of gloves for this part because sometimes this can spill when you turn your hands over, and I'll fill it up. Okay, so here we go. I got gloves on. I'm going to take this sample, put it into this titrator, they call it. The lab manual calls this a titrator. And again, hopefully not get any air bubbles. So the gloves are here because, I had dropper bottles before where there was almost no way to get it on my hands. Here, I'm actually going to invert this. It has a small hole in the top for the titrator, and some could come out on my hands. So I'm wearing gloves for this part. So put it in very tightly on the top. There's, like I mentioned, a small hole there. Hold it down. You don't want any air bubbles. So I'm holding it down and I'm flipping it over, and I'm going to pull this down so it fills up to the line. There's a line that says 0. I know it's hard to see. One thing too, before I even get started, this is pushed down all the way. So completely pushed down. There's no air in this. So put it in, hold it down tight. Here we go. Wish me luck. If I see any air bubbles, I will push it back in or remove it into a waste beaker and start over. The fact that I have so much here now, I wouldn't push it back into the bottle. I would put it into a waste beaker or waste glass in my case, because I'm in my kitchen. All right, let's check for air bubbles. I don't see any. There it is, no air bubbles in here. And the bottom of the syringe, like the plunger, is at the 0 at the very top, okay? Perfect. All right, let's get started. I know I've said this like 50 times, but let's get started with the actual titration. I don't need these gloves anymore because all my chemicals are ready and they're in self-contained, bottles. So one more quick cut, or well, maybe more, but here's another one. Okay, so, if you read the lab manual, and I really encourage you to do that on the PDF that I share, or using the PDF that I share, it does mention one important thing. If my sample right now is a pale yellow, I would not consider this pale. This is a bit weird, but I have canola oil here. I mean, that would be more of a palish yellow than this. This is almost orange. Okay. If it was pale yellow, I would skip a few steps and add my starch indicator. It's not pale yellow, so what I'm going to do is add my titrant, my sodium thiosulfate, slowly, drop by drop, until this is pale yellow. Then I'm going to add 8 drops of starch indicator. The starch indicator helps with this titration. It allows me to see the color change very easily. When I add the starch indicator here, it should turn blue, and my titration is done when this solution, it will be blue once I add the starch, is colorless. Okay, that's my goal. When this solution is colorless, clear colorless like water, I will read the amount on this, and that will be my ppm of oxygen. So I'm going to put the top in, make sure the plunger is in. Don't titrate it like this, make sure it's in. And I'm just very slowly going to press the plunger down and add, or shake it as I'm adding. Okay, just drop by drop. After a few drops, give it a good shake. Okay, and when it's pale yellow, I'm going to stop. So I've added, according to my burette here, 3 or 4 ppm. Again, drop by drop until the color lightens. I typically would do this flat on the bench, or I could do it back here, but I'm doing it in the air so you guys can see a little better. It's a little lighter now, so I think I'm going to add the starch indicator. I'll add a couple more drops. All right, I'm going to add the starch indicator and we will continue with this titration. All right, so take the top off my bottle here, add the 8 drops of the starch indicator. It should turn blue, fingers crossed. And if it turns blue, again, that's the starch with the iodine. We'll continue the titration until it turns clear and colorless. When it's clear and colorless, I read the ppm on my titrator, and that will be our oxygen. So 8 drops, and I think you should see this turn blue right away. Okay, there you go. Obviously, you want to mix this up now with the top on. So give it a little shake. Okay, mix it up as best as possible. Now, so again, fingers crossed, this should turn clear and colorless when I titrate it. All right, now here we go. Ready to titrate this blue solution with what's left in this titrator. I'm going to go drop by drop, shaking this as I go. If the liquid inside hits the top of the titrator, that's okay, I guess the tip, because any solution will be washed back in. So here we go, drop by drop, shaking as I go. You can see the color really fading. I don't think I'm very far away here from being clear and colorless. Maybe one more drop. Yep, there we go. Clear and colorless. Okay, so I'll try and read this value, and then that's it. That's the experiment. I will do this again one more time with the tap water, and then 2 more times with the bottled water. Okay, I kind of messed with some camera angles here. I can't really get it to show the best, but there is the bottom of my titrator. And if you read the lab manual, it mentions that every graduation or every line is decimal 2 ppm. So again, I know that's hard to see, but if I read it, I'm going to stand up and read it at eye level. I am at 8.246. So I'm in between 8.6, like exactly in the middle of 8.6 and 8.8. So that gives me a ppm, a parts per million, of 8.7. Okay, that's about as precise as I could get this. So that's an 8.7 parts per million. I'm going to do this again and share the results online. Now, I don't have anything else to show you with the experiment. I'm obviously going to test it again with some bottled water. This is our brand from McDonald's. Not a sponsor, but I'll take free burgers if McDonald's wants to give me some. So I'll test the parts per million of this twice, share all the results for your D2L quiz, and then you'll have to do a little discussion about it. So just remember for your discussion, things that affect ppm. I mean, there's different, it's in your notes, it's in this instruction kit. Things like atmospheric pressure, temperature, salt water can affect things like the dissolved oxygen. A big one that I've talked about already is temperature. The bottled water process is different than tap water. The tap water, is sitting out in a hot tank. It's been, pumped through pipes and is a little different than how we receive this water. So again, I'll leave it up to you. You can be creative with some of your answers here. But yeah, we'll test this. I'll post the results online. And that's the end of lab number 1. All right, if you have any questions, you know what to do. You can send me an email. We can chat on Zoom. Good luck and have fun.